we have a vector function f of x y equal x squared y I plus x squared y squared j, as you can see on your document. And we want to do a line integral of this, of f dot ds, around a closed path consisting of the four sides of a rectangle. Rectangle having sides parallel to the coordinate axes, and the points 1, 1 and 1.03, 1.05 at opposite diagonals, so that the other points, the other two vertices have the corresponding coordinates. So we're going to do this numerically. We want to numerically determine an approximate average value of the function, the vector function, so we need I and j components, on each of the four segments. Okay, so what is going to be very helpful is we evaluate the function at each of these 4 points, and then we can just average the values of the function over each interval. Okay, now what we're going to do then is we're going to take the average value of the vector function and dot it with the appropriate vector. Along this side, the distance is 0.03, the distance here is 0.05. Along this side, we're going to dot the average value of f with what? 0.03 times I. Here, what? Well, that's a distance of 0.05 in the j direction. We'll dot it with 0.05 j. Here, well, we're going from here to here, moving counterclockwise. We're going from here to here. We take an average value of the function and dot it by 0.03 times negative I. And here, by 0.05 times negative j. So we first want to get the values of the function. Well, it's very easy to evaluate the function. We just plug numbers in. If we plug 1 in for x and 1 for y, and actually I think I wrote this down incorrectly. I think this is minus x squared y I minus x squared y squared j. If we plug 1 in for both x and y, we get I minus j. That's very, very obvious. And it's really pretty easy to calculate these, just squaring the appropriate binomials, if you can do a little mental arithmetic, and get them right in your head. Now, I did that over here, but I was trying to talk at the same time or something and didn't get them all right, a little careless. But at 1.031, x is 1.03, so x squared is 1.03 squared, which is 1.0609, and y is still 1, so you're going to get 1.0609, which I rounded off to 1.061i. And then x squared is still 1.0609, which I round to 1.061. Y is still 1, so you still get the same number here. You're just going to have a minus on it. Okay, well, we can do those calculations all the way around the rectangle, and I believe we've got them right here. I did ask people to kind of check me out on these after I corrected a couple of bonehead mistakes over here. Okay, and here I made a chart, a table. Here's x, here's y, x squared, y squared. You see where we're going to use those. This is going to be multiplied by j. The negative of this is going to be multiplied by j, and this is going to be multiplied by I. At the points 1, 1, 1.03, 1, 1.03, 1.05, and 1, 1.05, the four vertices moving in the counterclockwise direction. Okay, so that's very easy to do. Okay. So we want to do the integral of f dot dr on the first path. Okay, and I don't know where okay, on path 1. Okay, on path 1, the average value of f, I said is 1.03i minus 1.03j. Okay, how did I get that? Well, the I component here is 1, here it's about 1.06. And we have that 1 on the end. I kind of discarded that. But the average between 1 and 1.06 is 1.03. And between negative 1 and negative 1.06 is negative 1.03. So the average value of the vector function is 1.03i minus 1.03j. Now if we average the I and j components between here and here on path 2, which is represented here, path 1, 2, 3, 4. This is what we get, this is what we get on path 3, this is what we get on path 4. It should be obvious to you that unless f has some very weird fluctuations, that in changing by 0.06 from here to here, x squared is going to not be linear, but it's not going to be that far from linear, so that we're going to be pretty close to the correct average value. And if you think about the linearity, you can look at the second derivative. How much does the second derivative change? Or what is the second derivative? How much change would that imply in your first derivative? And how much nonlinearity would that imply on a given interval? You can ask those questions, and the answers are pretty straightforward. We get a pretty good approximation because these intervals are small, and x squared and y squared don't have time to differ much from their values they would have along, say, their tangent lines. Now, don't want to get into a big discussion of that. We've had that discussion. Okay, so in any case, on 1 then, the integral of f dot dr, well, what's dr from here to here? Well, it's a straight line in the I direction, distance 0.03, and we're going to, of course, approximate that by a delta r. The delta r on this path is going to be 0.03 I. That'll take us from here to here. We dot that with the average value of f, so we do f av dot delta r, and right there is f av, and right here's our delta r, and we get about 0.0309. Okay, well, we do the same on each of the other 3 intervals. And you should, at this point, if you didn't get it the first time, you should just turn off the video, write down the function, write this down, and figure out the next interval and the next and the next before you look at the results. Anyhow, we get the results that I give you here. Now, the big thing that's going on here is that the integral around this path is going to depend on the difference between the integral on this path and this path. Okay, now we can break it down that way. Call this path 1, call this path 3. Okay, we take the sum of the integrals over path 1 and path 3. Of course, path 3 goes in the opposite direction. So we'll have a negative for path 3 and a positive for path 1. And our changes in x and y are small, but they're not so, and when they're really small, we don't expect the integral from here to here. We don't expect the values of our function between here and here to vary much from the values between here and here. So we expect to get a pretty small difference between this and this, so that when we add this to this, going in the opposite direction, we're going to get something pretty small. Now, hopefully you understand that. And it's the same here. We're going here in this direction, we're going here in this direction. What we get in this direction should be pretty close to being equal and opposite to what we get in this direction. So let's just see how that works out. Let's compare path 1 with path 3. See if they're equal and opposite. They would be if the values of the f function didn't change at all between here and here, but they do change a little bit, and that's going to give us a non-zero difference. So, well, our integral in path 1 is about 0.031, let's say, and here it's about negative 0.032. Okay, well, the magnitude of this and the magnitude of this are pretty close, so that when we add them, we get something pretty small, 0.0015. Okay, so the net contribution to the integral around this path from the integral here and the integral here is negative 0.0015. Now, net contribution, this path and this path, subpath 2 and subpath 4 if you like, turns out to be, well, our integrals are negative 0.056 here and positive 0.0525 here. If we add these, again, we get a negative 0.0035, giving us a total of about negative 0.005. So the integral all the way around here is pretty small, about negative 0.005. Now we want to think about just what it is that makes this bigger than this, or makes this differ from this, and what makes this differ from this. If you think about it, along this path, the x values are the same, although we're moving in the opposite direction as they are here. So at any point here, the x value is the same at the corresponding point up here. So it's only the y values that cause the change between, that cause the integral from here to here to not be equal and opposite to the integral from here to here. And similarly, it's only the changes in x, because y values are the same, corresponding points. It's only the changes in the x values that cause this not to be equal and opposite to this. We're going to see what the implications of that are, and we're going to get a really pretty astounding result out of this. Okay, we'll see what the result looks like, and we'll see one of the great, beautiful, most beautiful theorems in mathematics comes out of this idea. So we'll go on with this in the next clip.